Welcome to Radioactive Decay. Today we're going to be talking about a mastodon. So let's start with the definition of what half-life is. No matter how much you start with, half-life is the number of years it takes to have half of that. Doesn't have to be years. Some isotopes are short in a matter of days, but mostly we use carbon-14. Its half-life is 5,720 years. So if you start with 100 grams, after that many years, you'll have 50 grams. Or if you start with 6 grams, after that many years, you'll have 3 grams. It doesn't matter how much you start with. It's just a half after that many years. So in 1970, Amos discovered some teeth and jawbones from a mastodon. I found this mastodon jawbone on sale for eBay, so you can buy that and hang it on your wall if you wish. Anyway, they determined that the bones had lost 77.2% of their carbon-14. And we want to figure out how old the bones were at the time they were discovered in 1970. We will start with the typical standard exponential equation here, where the ending amount equals the starting amount times e to the kt. We don't know what k is yet. We know what t is. The half-life is 5720, and we don't have a starting amount or an ending amount, so that's kind of a problem. You would think, well, we can't do this problem, but we can because we know what half-life means. So half-life means half. The ending amount is half of what the starting amount, and we don't care what those amounts are. So we can put anything we want in there, and we'll just put 5720 for the t. So here we started with 2 grams, ended with 1 gram. That's going to work. Could have used 50 and 25, doesn't matter. So now we're solving for k. And we take the natural log of both sides to get that k out from the exponent, so we can end up with k equals. Because natural log and exponential function are inverse functions, they undo each other, and we end up with the natural log of 1/2 equals 5720k. Usually I insist on fractions, but in a word problem, decimals are fine. So that's our k. If you put it in your calculator, you get a horrendous number, which is generally going to happen for carbon-14. So here it is. And it's negative, showing that we have a decay situation. So that's what it looked like on my calculator. I'm going to write it in regular notation instead of scientific notation. So it looks like that. I ignored the negative sign at this point. I know that it's a decay problem, and all the negative does is say decay. Okay, so that's our k, and we really need to watch out with rounding in this case. When you've got a large number like 5720 and you've got a tiny number like this, or a large amount of grams that you're dealing with, whatever, whenever you've got something this small, if all the numbers are small, it's not a huge issue. It's when you've got a big change between different aspects in the same problem, you're going to have some rounding problems. So I want to do this showing what it looks like with different levels of rounding. But first, let's write the problem down. So we're back to our original equation. We're going to just say we started with 100 grams. We can do that. And 77.2% had been lost. So the ending amount is 100 minus 77.2 grams, and the starting amount was 100 grams. So we end up with this. And now we take the natural log of both sides. And now we're going to use those three different values of K to see what happens with the rounding. So for the first one, we're going to use K equals 0.0001. So here's K, and the T that goes with that is 14,784 years. If we just add one more decimal place onto that, the time changes to 12,320 years. That's a huge difference for just one decimal place. If we use the whole thing that we started with, that number, we get a time of 12,200. So you can see that there's not as big a gap there. So as you keep increasing, your accuracy gets better. So be careful with that when you do these problems. And that's it for radioactive decay.